So today we're moving into the study of vapor power cycles, and this is the predominant way in which we generate electricity, not the exclusive way, not the only way, but it's the predominant way we generate electricity in the United States and throughout the world. So when you have a substance which undergoes a phase change, goes into the vapor state, from liquid to vapor state, it's like boiling. Then you take that substance, pass it through a turbine, you expand it, it extracts energy out of the working fluid, and the turbine is used to turn a shaft which turns an electric generator to make electricity. So it's a very common power cycle. Do we have vapor power cycles that operate our automobiles? No, that's a different cycle. It's a gas power cycle, auto and diesel cycles. We'll study them later. But stationary power plants often are based on a vapor power cycle. To begin, we'll review the Carnot cycle, and the Carnot cycle can be implemented with a working fluid that undergoes a phase change. It doesn't have to be an ideal gas. If you look back in Thermo 1, introduced the Carnot cycle primarily thinking about an ideal gas. But you can also look back in Thermo 1 in that previous section and you'll see, oh yeah, we did talk about the Carnot vapor power cycle. And that helps us understand what we call the ideal Rankine cycle, and then we modify the ideal Rankine cycle to be actual Rankine or vapor power cycles. So just a quick review of this Carnot. So it's named after a man whose last name was Carnot, Sadi Carnot. These are the years he's lived. That's a long time ago, right? 1796 to 1832. And when you get older, you start taking the difference between your birth year and last year on this earth, and you find that he only lived a short lifespan of 36 years. So he did a lot of work if we're still talking about him today. And he's in every engineering thermodynamics textbook. So he was a French engineer. He wrote one book, one piece of work. He published it in 1824. It was Reflections on the Motive Power of Fire. So he's thinking about how you burn things to turn things, which is a novel concept at the beginning of the Industrial Revolution. Before, if you wanted to turn something, lift something, push something, it was either human muscle or animal muscle. That's about it. You did have waterfall, and you did have capturing the energy in a big water paddle wheel, grain mills and stuff. But other than that, it was muscle power. But here, at the start of the Industrial Revolution, you burn something, fire, to turn something, the motive power of fire. So here's a picture off of Wikipedia. And here is the text. You can still purchase that English translation of that French paper. I think it's put out by Dover, been put out for many years, and so you can still read it. It's not, it was done a long time ago. It had some great things in it, but it's not spot on. It wasn't perfect in comparison to our current understanding of thermodynamics. But so he idealized, which was a big step forward, the heat engine. And the two main points where the efficiency is a function only of the two temperatures of the reservoirs which operate the heat engine. So you have a device, it's called a heat engine, and you have a thermal reservoir and a thermal reservoir, and it supplies some heat, and it has to reject some heat, and the goal is to produce power. So convert as much of this QH from the high temperature reservoir into work which means that you need to minimize QC into the low temperature or cold reservoir. Also, the idea that the maximum efficiency obtainable does not depend upon exact nature of the working fluid, it depends upon those temperatures. So everybody should remember that the Carnot efficiency, the maximum thermal efficiency for a heat engine operating between two reservoirs is 1 minus Tc over Th, where Tc is an absolute and Th is an absolute. There's a few things you can almost say, oh, the 50+% probability will be a question that must, on the FE exam, that you must use that relationship. You must understand and be able to use it in one way, shape, or form. Think about that. I just helped you a little bit, right? You're going to take the FE exam? There you go. Don't forget that equation. So in general, I'll just re-sketch that. You have the heat engine. You have the thermal reservoir, TH. You have the thermal reservoir, TC. Heat transfer, QH. And heat transfer, QC. And the work, W. Let's take a look at the first law, also known as an energy balance for this system. So if I take a look at the heat engine as my system, what do we see? We say that QH is an in, and work is an out, and QC is an out. True? Is that the first law, energy balance? Let's write the second law, which is not an energy balance, but an entropy balance for that heat engine. So do we have any entropy coming in with QH, the heat transfer in? Yes, we do. What is the model, the analytic expression for how much entropy is transferred with that Q? True or false? Is all of that heat coming in from the constant temperature thermal reservoir at TH? Yeah, all of it's coming in at one boundary temperature. It's all at TH. Okay, do we have any entropy out with the work? No entropy transfer with. How about any entropy out with the QC? Yeah, TC. Do we have any entropy generation, which I'd put over here? Well, it's a Carnot. It's maximally efficient. It's minimum irreversibility. You play that game and that's zero. There's no irreversibilities. There's no entropy generation. Is that a good statement then of the second law? And can we combine these so that if I say the thermal efficiency is defined as how much of that energy goes out in the form that I want, goes out in W, divided by how much of that energy came into the system to make it work. That's Q sub H. Q sub C is just something that has to happen. I have to throw some of that heat transfer away. So Q sub C, we don't like the large Q sub C. We had to pay for and provide the system to make it run Q sub H. So we then use the energy balance to replace W. So W is Q sub H minus Q sub C. Is that true? So that's 1 minus Q sub C over Q sub H. True? And at this point, we use the second law to replace the ratio of Q's by ratio of T, 1 minus Tc over T sub H. You don't have to memorize equations. So it's nice to recall those equations, but look at right here it is. Isn't that true? So all you had to do is know the definition of thermal efficiency, first law, second law, know that for Carnot, there's no entropy generation. What are the 4 processes that go inside this box, this heat engine? Typically 4 things that are going on inside that heat engine. What are those 4 things? Well, we're going to compress it. Compress. Compress the working substance, adiabatic. Adiabatic compression. What's that mean? No heat transfer. And we're going to do that internally reversible. So all of these 4 are going to be int rev. If I say it's int rev, that means it's no friction, it's no entropy generation. And if I have its adiabatic compression, then there's no entropy transfer with heat transfer because it's adiabatic, no heat transfer, hence it's isentropic. Isentropic compression. Okay. Followed by expansion. Okay, but what type of expansion? Isothermal. So if you have expansion and it's isothermal expansion, you're probably dumping heat in, you're bringing with it some entropy, the heat transfer coming in, but it's all coming in at one temperature, the high temperature. Okay, you have to bring in heat, you have to bring in energy, so there's entropy coming in with that heat at high temperature. What's the third? Well, we're going to expand. That's adiabatic. What happens, think about that. I'm continuing the expansion, but instead of having heat brought in, heat transfer in, it's going to be adiabatic. Well, if I could think about both a closed system or an open system. If I think about the closed system, well, you're expanding, it's doing work, there's no heat being brought in, that temperature is going to fall, and it does fall. And so at the end of that, it's down at a low temperature. You could put it through a turbine, that's an open system analysis through a turbine, and you find that the temperature drops here in this adiabatic expansion. All right, and the very last, we have to compress it, isothermal. And that's at TC at the lower temperature. So Carnot cycle made of 4 either processes like a closed system or flow through 4 components in which you have this description. You compress it adiabatically, expand it isothermally, expand it adiabatically, or compress it isothermally. All right. So how do we implement this for the Carnot vapor power cycle? Well, you'll have a device called a boiler. You'll have a device called, I'm just going to show it as a box, turbine. A device, and the fluid flows out of the boiler into the turbine. Then out of the turbine, it flows into a device called a condenser. And then it flows out of the condenser into another device, and I'm going to say it's a pump. We talked last time, what's the difference between a pump and a compressor? What is the condition of the substance coming into the device? Okay, both of them increase the pressure of the working fluid. But one, the pump, that word is used to describe something that increases the pressure of a liquid. A liquid is incompressible. It doesn't change volume. Compressor, it increases the pressure, but it's actually changing the volume as well because it's a compressible working fluid. So I know that I'm going to be changing the volume, changing the specific volume of the fluid going through this quote-unquote pump for this Carnot, but I got to call it something. The device is to increase the pressure. I could put pump slash compressor. Fine. All right. And what we have to do is we have to introduce states. It's convenient to maybe introduce state 1 here, introduce state 2 here, state 3 here, state 4 there. So the fluid flows through the boiler, then through the turbine, then through the condenser, then through the pump. And what we do is we analyze each component. We'll do an analysis of a control volume around the turbine. We'll do analysis of the control volume around the condenser. Same thing around the pump and around the boiler. So we're going to, I know that you have to get in your mind straight. Is this analysis that I'm about to perform, is it for a closed system or an open system? Yeah, it's for an open system, because in your mind you want to be able to apply the correct equations and not get tripped up. How many students get tripped up? Yeah, they get tripped up, right? So you want to get that straight in your mind, that you're going to analyze the turbine, the condenser, the pump, the boiler. Okay. So what type of analysis would we do for the turbine? Well, what is the turbine? Isn't it a work-producing device? And what we'll do is we'll use a lowercase w subscript t. Lowercase w instead of cap w. What? Why lowercase w? What's the syntax? What's our notation? Specific work. So this would be the same as the power out the shaft per unit mass flow rate through the device. True or false? Yeah, so it's the power out the shaft of the turbine per unit mass flow rate. So I know the first time we see that, that's not the first time you've seen it. I'm helping you review the material you know. It throws you for a loop, but the units on this are kilojoules per kilogram. How much work is produced by the shaft, going out of that turbine per kilogram of steam going through the turbine. Or you could think about it being kilowatts per kilogram per second, and a kilowatt is a kilojoule per second. So the per seconds cancel. And so you're left with that kilojoule per kilogram. Okay, so we do that first law. We hone in on the property enthalpy. We neglect changes in kinetic and potential energy. It's adiabatic expansion. There's no heat transfer. So Q dots equal to 0. Sometimes we'll do a little hash mark like that saying, oh, it's a well-insulated turbine. And so when we do all of that, what do we find? Let me kind of erase some of this stuff so it cleans it up a little. What do we find? H1 minus H2. True or false? Okay. That's true. Is H1 greater than H2? Is the enthalpy of the steam coming into the turbine greater than the enthalpy of the steam going out? It is. It is. Think about enthalpy as energy content of the working fluid. It's internal plus flow work. It's energy content. High in, low out. It had to go somewhere. It went out in the shaft. That's what you want. Now we take a look, and we're going to draw the direction of the heat transfer in the direction that it actually goes. It actually goes out of the working fluid in the condenser. Where is it going? It's being transferred to another fluid, maybe the air in the environment, maybe a lake water, maybe river water, maybe ocean water, but it's being rejected out somewhere into some fluid in the environment. So it's coming out of our working fluid. So we're going to draw it positive going out. We're breaking or deviating from our sign convention. For the control volume, typically, Q is positive in. This direction, QC is positive out. I have a diagram. I show the direction. I override my sign convention. Okay, so this now is going to be H2 minus H3. Which enthalpy is greater? State 2 or state 3 enthalpy is greater? 2 is greater. because it's coming in with higher enthalpy and it's transferring some energy out in the form of heat transfer out of the working fluid while it's condensing, and then it comes out at a very low energy state, a low enthalpy at state 3. What about the pump? Well, that's a device that you're going to have to supply a shaft and an electric motor to drive it. So the W of the pump is equal to H something minus H something. Well, is it H4 minus H3? Which enthalpy is greater? 4. 4 is greater, so H4 minus H3. And that's a positive in. I know I'm going fast. You have to go slow, especially when you're solving problems for the first time. Nothing, that's just what it is it takes you a while to learn. Learning is hard work. How about for the boiler? Q sub B, subscript B for boiler, equal to H. Which H is higher, H1 or H4? H1 is higher because you're dumping heat in, bringing heat in, bringing energy in the form of heat transfer into the working fluid. Okay, so there you go. Those are all of our enthalpies. Now, what we want to do is we're interested in plotting this on a property diagram. How many property diagrams have you studied? You studied, kind of rattle them off. There's a couple things that I think it'll help you as you study problems. Rattle off from memory a list of properties. A list of properties. What's number one property? First on the list, top of the list. Temperature. Another property, second on the list. Pressure. Another one. Specific volume, internal energy, enthalpy, entropy, flow exergy. You could keep going. You could put in any specific heat. You could put in, a couple more properties, but I'm thinking, like expansivity or compressibility, but some of those we haven't covered yet. Are there any other properties that we have already covered this semester? Oh, ratio of specific heats. It's just a property, that's all. Is there any others that I'm trying to think of? It helps you sometimes when you're lost, say, I know this state, I need to fix this state and get the enthalpy from that state. That's what I want. I know the state principle, 2 independent intensive properties, fix the state. Theoretically, I'm able to then get the property that I want. Which 2 do I know? Make the list and start checking down the list. All right. The other thing, from memory, knowing what turbine, condenser, boiler, and all that do, that's great. But also property diagrams. Diagrams. How many diagrams have you studied that we studied in thermodynamics? A couple of them. Give me one of them. The pressure volume diagram is a big one. A temperature entropy diagram. That's great. The TP, sure, or temperature pressure diagram. We had the PVT surface. PVT surface. I'm sorry? Well, just look at diagrams. What we want to do right now is, these are the 2 big ones. Later we're going to get a pressure enthalpy diagram, and you could also get I'm trying to think of it, pH and not a TH. We already had the TS. Well, anyway, pH is another big diagram. We'll get to it later. Which diagram do you think I would like to show this cycle on? Okay, let's go ahead and try a TS, temperature entropy. Now, it's undergoing a change of phase. True? True? Well, for the vapor power cycle, for this Carnot vapor power cycle, I'm going to put a dome on the temperature entropy diagram. At the top of that dome, what's the name of that point? Critical point. Every state off to the right from the critical point, that line making the top, the dome, what is the description of every one of those states? It's saturated vapor. Saturated vapor, true? Then every point going off to the left on that side, that's all saturated liquid. Saturated liquid. Okay, good memories. Now I lost my diagram here. I'll try and sketch it back. All right. Now on a temperature entropy diagram from memory, what does a line of constant pressure look like? Inside the dome, it's flat, it's straight across, it's horizontal. True? And so here is a line of constant pressure. Like that. That's a pressure. That's a high pressure. Show me another one at low pressure. Here's one. I'll try and change color. Comes up, hits, goes straight, flat, cross, hits, goes up. That's a low pressure. So at what point is it saturated vapor and at low pressure? Is it this point right here? Yeah. Where is it the low pressure and saturated liquid? Is it that point right there? Yeah. Where is it high pressure and saturated vapor? Right here? Saturated vapor, high pressure, and saturated liquid, high pressure. True? Okay. Now, this is a very funny thing. You may recall it about the Carnot. But all of the heat has to be brought into the cycle at a high temperature. Let me try and draw this at a different color right here. So, think about this high temperature thermal reservoir. You can't have high heat transfer coming in from TH going into a cold fluid in the boiler. The fluid in the boiler has to be at TH. Has to always be at TH. That seems like an oxymoron. Seems like it's impossible. It can't be done. It can be done. How do you get heat to continue to go into a working fluid without the working fluid changing temperature? And the temperature of the working fluid in the boiler stays TH. That doesn't make any sense, Professor. This is crazy. I want my money back. The thermodynamics textbook doesn't work. No. What happens? How does that work?
The energy is being transferred into state change rather than temperature change.
Perfectly said. It's changing the phase. It's changing the phase from liquid to vapor at constant pressure. So, what do you think would be the kind of the maximum coming out of the boiler and the minimum coming out of the boiler? Both of them are at high pressure. Both of them are at high pressure. State 1 and State 4 are on the line of pH, the high pressure line. But where is State 1? Where is State 4? State 1 is the maximum to the right. State 4 is the maximum to the left, but it has to stay at TH. Right here is TH. So this is State 1, and this is State 4. So State 4 is saturated liquid at the high pressure. And State 1 is saturated vapor at the high pressure. True or false? Did I put State 1 and 4 correct on the diagram? Good. Now it's a challenge to find State 2. Where is State 2? It's at the low pressure. I should have emphasized that. I have two pressures for this problem. The two pressures go right here. Cut through. The turbine and the pump. Everything on this side of that line is high pressure. There's only two states on that side. It's state 1 and 4. And we just said, hey, state 1 and 4 are both high pressure. Everything on this side, there's only two states down there, the whole condenser, right? The outlet to the turbine is the same as the inlet to the condenser. The outlet of the condenser is the same as the inlet to the pump. State 3 and state 2 have the same pressure. It's low pressure. So, I forgot to emphasize that. Back up a little bit. Now that I know that I'm going from state 1 down to somewhere on that low pressure line for state 2, where is state 2? It's directly below. It's directly below. That's state 2, isn't it? What do you mean it's directly below? Well, we picked to do this on a temperature entropy diagram. If I do a second law analysis around that turbine, it's adiabatic and all internally reversible. It's isentropic flow through that turbine. The inlet entropy is equal to the exit entropy. True or false? Yeah, true. Now the hardest one. I'm going to condense somewhere and I have to stop condensing. Should I stop here? Should I stop here? Should I stop here? You know, let's do clicker question. A, B, or C. Where should I stop the condensing process? Oh, no, it's a clicker question. Everybody has their clickers, and you have 25 seconds to answer. Very good. All right. Okay. If you look, state A, nobody was fooled by state A. True? You condensed a little, but you didn't condense enough. You need to keep condensing. Okay. State B. Visually, some people, 68% of the class said, I think we need to stop condensing at B. What do we do? What do we do? Why do we stop condensing at B? Well, because I need to put it through this magic device. The professor was sitting there saying, I don't know if I should call it a pump. I don't know if I should call it a compressor. It's something that some magic device is going to boost the pressure. It's going to be doing it internally reversibly, no entropy generation, and adiabatically, hence isentropically. Constant S, boost. Constant S. So if I stop at B and I say go and follow a line of constant S going to increasing pressure, I get magically to state 4. See, those students, 32% of the class, are a little ahead of you. Yeah, they're like an accelerated. They're already reading ahead. They're thinking about the next section, the Rankine cycle, the ideal Rankine cycle. All right? So for them, they need to save that answer. They'll get it right next time. Okay, so there you go. You stop at this point. So that point is state 3. There's 3. Then you go up through the pump to state 4, through the boiler to state 1, through the turbine to state 2, down to the inlet to the pump through the condenser to state 3. So there's the cycle. What does that cycle look like, the shape on the TS diagram? Looks like a box. Looks like some sort of rectangle. I didn't say a square box. It's just a box, okay? Two sides, both sides. There's, you know, they're parallel to each other, and it's a 90-degree turn on that temperature entropy diagram. Okay. What temperature is the working fluid from state 2 to state 3? TC, the low temperature. What is the working fluid from 4 to 1? TH. So all of the heat is brought in at TH. All of the heat is brought in TH. All of the heat is rejected at TC. True? True. All right. And we already worked out the thermal efficiency for that cycle. We want to solve a problem. So when you think you understand the material, solve a problem. When you solve a problem, start with a clean sheet of paper and the problem statement. And don't fall into the trap of reading the solution that somebody else worked out and think that's learning. It's not learning. Because unfortunately, during exam time, I don't give you a solution, say, please read it and see if you understand it. Right? You have to solve your own problem. So, water is the working fluid in a Carnot vapor power cycle. The boiler operates at 8 megapascal and the condenser at 20 kilopascal. It sets that high pressure and low pressure. The high pressure is 8,000 kilopascal, low 20 kilopascal. Determine the work developed by the turbine and the pump. So we're going to look to solve for WT and WP. Both I want to be positive quantities. One is the positive work out of the turbine. One is the positive work into the pump. Both per unit mass that flows through it. Heat transfer in the boiler and the condenser. QB positive into the boiler. QC out of the condenser. Positive out of the condenser. Then the thermal efficiency, eta, Greek symbol, is our typical thermal efficiency. What's our thermal efficiency defined as a ratio of what we want? What do we want? A large net work out. What do we have to pay for to drive the system to make it work? QB, Q into the boiler. Is that work net what comes out of the turbine minus what goes back to feed the pump? Is that true? It is true. Okay. And then the back work ratio. Well, how much that came out of the turbine has to go back to feed the pump? That's the back work ratio. Both of them are works. One is what had to go back into the cycle. Instead of everything that came out of the turbine, we'd love to, just make electricity and sell it and make gobs of money. But unfortunately, some of that has to go back to make the cycle work by feeding the pump. So the back work ratio. So this is a Carnot cycle. So in our mind, we think of our 4 components laid out, the working fluid flowing through those 4 components, state 1, state 2, state 3, state 4. This is our boiler, this is our turbine, this is our condenser, this is our pump, and the directions of the heat transfers. This is Q sub B, this is Q sub C, this is WT, and this is WP. True? Okay. Now, you also probably want to sketch from memory that property diagram, the temperature entropy. Think of 2 temperatures, TH and TC. Put a dome on it. Put lines of constant pressure. Put lines of constant pressure. And go ahead and put our state 1, state 2, state 3, state 4, and you know which direction the cycle's going. All right. And we know that if I want to calculate this W sub T right here, I really want to get H1 and subtract H2 from it. If I want to calculate the work, maybe I should put that elsewhere. Maybe I should put it over here. If I want to calculate the work of the turbine, I need the enthalpies, H1 minus H2. If I want the work of the pump, it's going to be H4 minus H3. True or false? Did I write both correctly? Or did I make an error? Correct or incorrect? And then if I want to calculate the Q in the boiler, H1 minus H4, and the Q in the condensers, H2 minus H3. How easy is it to get one of those, swapped around? And so, oh no, I think the boiler is H4 minus H1. It's very easy. So you have to get them straight. H1 minus H4. True? So I think this is what helps me is I look at and then try to go through the process and saying which one is greater. You know, which is my greatest H? Probably H1 coming out of that boiler. And then H2 is less. And then H3 is even lower than H2. But then the pump boosts it back up a little bit. H4 is higher, or a lot higher. But H1 is the highest of them all. Okay. Probably make a nice property diagram or table to organize your work. So if you make a table, what you want to do is say, okay, what state do I have? I have states 1, 2, 3, 4. Later we'll have state 2 and 2s and 3 and 4 and 4s, etc. But right now it's all internally reversible, so I don't have this two states where one is isentropic compression or isentropic expansion from the previous state. And then think about putting my most popular or common properties. Start with pressure, put them all in kilopascal. Temperature, put them all in degrees C. Then I may put a quality in there, and then I'll put an enthalpy in kilojoules per kilogram and an entropy in kilojoules per kilogram Kelvin. You could put volume and you could put internal energy as additional properties, but after you solve a few of these problems, I really have to hone in on my S's and my H's and quality. All right, let's fill in this property diagram, this table for the properties we know. Do we know the pressure at state 1? That's the high pressure, right? Put 8,000. Did I do that correct? 8 megapascal is 8,000 kilopascal? Good. How about state 2? 20? 20? 8,000. So we have all our pressures. Good. Now, what about state 1? That's where I kind of put a little piece of information over here, is what helps me fix the state. For state 1, it's that the information is its saturated vapor at the pressure given. P and saturated vapor, the two pieces of information that allow me to fix everything about state 1. Do you see that? All right, so how do I find this temperature? Tsat at that pressure of 8,000. Now this is confusing. So we have a pressure 8 megapascal. Good. And I said it's 8,000 kilopascal, and everybody said, Professor, you did that property conversion correctly. I flip to the table, I say I want to use the steam tables and the pressures given in BAR. All right. I'm going to pause right now, and I'm going to walk around the room, and I want people to write down what the pressure is from your memory. From your memory. Make that pressure conversion and tell me what it is in bar. This is one of those pressure conversions you need to get down with confidence if you haven't done it already. So when we convert this, what was the consensus? 80 bar. Some people had, oh man, I don't know. I don't even want to repeat some of the answers. But this problem of pressure conversion is so tricky that the textbook in the next edition, the newer edition of the textbook, which I don't have a copy of, actually put a little convenient reminder on how to convert pressures in the table A2 and A3. True or false? True. They didn't have it in the 7th edition. If you look at that appendix, that's the 6th edition. It doesn't have that little pressure correction or helpful reminder. True? Is that the newer one? Yeah, that's the 8th edition. So that's just, why did the publisher do that? Well, the author of the textbook said, I'm getting, a lot of faculty to say the students mess up the simplest of the simple pressure conversions. Or maybe they do have it in the 7th edition. They added it maybe in the 7th edition. So this needs to be 80. So when you come in, if you have your table, what is Tsat at 80 bar? Pardon? 295 degrees C. All right. Now, what about temp? Let's finish it out. At state 1, the quality. What is H at state 1? Is it H of G at the 80 bar? Sure. What number do you get for that? Around 27 something? 2758? Any point on that? 2758.0? All right. How about S? 0.7432. Got it? Everybody know where those numbers came from? Okay, good. Let's go to the next line. What is the temperature at state 2? Well, this is the same thing. I've got a pressure. They didn't give it to me in megapascal. They gave it to 20 kilopascal. I need to get that into bar correctly because that's the unit of pressure that's in the tables. My steam tables, because I'm going to look up Tsat. All right, so what is that in bar? 0.2 bar? True? Good, excellent. So what's Tsat at 0.2 bar? About 60. 60.0 something. 06, 60.1. Good enough. What about the quality at state 2? Do I know that? Well, look at where it's at. Visually, it's somewhere where the quality is less than 100%, but I don't know what it is. I'm going to calculate it. It's really, I should finish this up. What helps me fix the state 2? Knowing the pressure and S. P and S. I do a little work to find S, but that's the second property. How do you like that for terminology? It's my other property that helps me fix the state. I know pressure, good. That's given to me. I then can calculate S doing a second law analysis around that turbine. It's going to be 5.7432. I then do some work. I get quality next. The quality is around 0.694, and it gives me an enthalpy around 1888, somewhere in that vicinity, okay? Do you know how to do those steps? Everybody? Professor, are we going to have lots of time for exams? No. If the first time that you're honestly working a problem is on an exam, you're in trouble. How many students come in and they're in trouble? Why? They didn't do one problem. No, honestly, they didn't work one problem. They think they're going to kind of pick it up and, learn how to do it during the exam. Recipe for failing the class. All right, now, what about state 3? Do me a favor. Go back and fix state 4 first. Sometimes you can go sequentially through the table. This is one of those cases where you can stare at it and say, I know 1, I know 2, I'd like to get 3. Without fixing 4, good luck. Go to get state 4. 4, you know that it's the pressure and it's saturated liquid, true? So it's 295, quality is 0. You get an enthalpy of around 13, 17, and you get an entropy around 3.208 or something. 3.207? 7, okay. Then you 3.2068. That lets you fix the entropy at state 3. So I know the pressure and the entropy, hence the temperature is saturation, the The quality is around 33.6, and I get that enthalpy, which is the property that I really need, around 1043. Okay? Okay. Okay. What I do is I use equations. There's a lot of equations that we should know. One of them is if I have the, I'm going to give you a long answer to this question, okay? If I want to calculate the specific volume of a two-phase mixture where I know V sub F and I know V sub G, does that equation look familiar? And what is that X right there? Quality. Can I do the same thing for H? Can I do the same thing for S? And so I can use one of those equations for this problem for both of these qualities. Since I know the S at state 2, I have to get SG and SF at state 2, or at that low pressure. And then I can get the quality at either state 2 or the quality at state 3, knowing that I have S2 minus S of F divided by SG minus S of F. It's interpolation with respect to quality. Once I know that, I use this equation to get the unknown enthalpy. True? I'm curious, how many people have ever taken a foreign language class and the teacher won't let you speak English in it, that you have to speak the language that you're supposed to learn? Either it's Japanese or Spanish or something. They did that? Only speak Spanish. Yeah, that's interesting. So anybody else had that experience? Couple? Yeah. So anyway, this is like thermodynamics. We're just trying to speak the language. So there's a lot of jargon in it. Hopefully all of this made sense. It'll make more sense if you practice. All right. Does that all look good? Then what we do is we come in and we solve for the work of the turbine. Just find that H1, that H2. We already found it. Make the difference. All of these are now easy. You have the H's. True? And then you just go back and you calculate the efficiency and you calculate the backwork ratio. The answers are on the next slide. Can I move to the next slide? Let's move to the next slide. And so this is for the Carnot. What I do is, there's the state 1, 2, 3, 4. This is a little information about how to help me recall what was the key information to fix that state. Oh, it was pressure and saturated vapor. Oh, P and S, pressure, saturated liquid. And then here's the pressures, temperatures, quality. I threw that in for fun because it's nice to see how things expand and change volume. When you go through that turbine, look at this. Is there an expansion of the steam going through the turbine? Yeah, a little bit. Quite a bit, right? And then what happens is you go through the condenser. Well, it's condensing, it's all turning in liquid state, and so there's, and then what happens is from this, it's not all liquid, I'm sorry. This is still a two-phase mixture. It still has quite a large volume. And then from 3 to 4, it goes through that pump, and so it's being compressed quite a bit. Okay? But these are the critical H's and S's. Here are the work, heat transfer, work of the pump, heat transfer in the boiler, the network. I always do this whenever I'm solving a problem, is if I've got all the W's and all the Q's, I'll calculate work net and I'll calculate Q net. Why? Because if they're not the same, what do I look for? If these are not the same number, what do I look for? I look for an error. I have an error somewhere. For all engines, heat engines and other things, the net work of the cycle is equal to the net Q of the cycle. Okay? And I know that the work net out is equal to the work of the turbine minus the work of the pump. And the Q net in is equal to Q boiler minus Q out to condenser. And for this problem, great, they're the same numbers. I have a little more confidence that my solution is correct. But if they were not the same answer, I am absolutely confident I have an error. Somewhere, go find it. All right, back work ratio, 31%. That's a high back work ratio. 31% of what comes out the turbine, a third of what comes out the turbine has to drive the pump. That's too high. We don't like that. Efficiency, 41.4%. How did we calculate this efficiency right here? Well, we said the efficiency is the work net divided by Q of the boiler. This is a Carnot cycle. Professor, could I use this simple little analytic expression, 1 minus TC over TH, and calculate the efficiency, and will that give me the same answer? What do you think? Well, yeah, it does. But when I use the TC and the TH, I know this is the TC, 60 degrees C, but don't put 60 in, put 60 plus 273.15. If you want all those digits, put in temperature conversion to 5 significant digits. And then the same for the TH. Okay? Isn't that incredible? The 3 significant digits, the efficiencies, are spot on. These are one of these things where I pause, ask you to think about that. This is almost unbelievable. Right? All of these enthalpies, looking up the property data, and all these entropies, looking them up and making the quality calculation and all that. And it gives me the same thermal efficiency as this very simple analytic expression, 1 minus TC over TH. That's true. First time I ever did it, I still remember. Ooh, wow, this is unbelievable. All that work gives me the same efficiency as just a quick equation. Yes, sir?
Is the backward ratio the work of the pump over the work of the turbine?
That's it. That's all it is. And so you can check these numbers here just to see. Take this work of the pump, 274.08, and divide it by 870.2, and you should get 31.5%. Yep. Okay. So there you go. That's all prelude. That's all introduction to studying how we actually make this cycle work. But at this point, one of the themes comes out. How do I, as an engineer, want to improve efficiency? How do I do it? How would you do it? Your first day on the job, improve the thermal efficiency of this power plant. How are you going to do it? Well, TC goes down or TH goes up. Isn't that the recipe? All right. Well, embedded in this whole cycle is, what do I need to do here? Take TH and go up. TH is the temperature of that working fluid. How do I get a temperature maybe 300 degrees C, maybe 350 degrees C? How do I get a higher and higher boiler pressure? Oh, I gave away temperature. You have to have a higher and higher boiler pressure. Go up to 10 megapascal. Go to 12 megapascal. Wouldn't that do it? There you go. Increase the boiler pressure. Good recipe. Until things explode. Then you back off. Okay, but that's what happens. What about lowering TC? Oh, try to throw it away at something less than 60 degrees C. Throw it away at 40 degrees C. But usually you got to throw it away to the environment. Average day, surface of the earth, lake water in South Texas made, 25 degrees C. You're stuck. Well, Professor, I'd like to go to 20 degrees C. What are you going to do? Import ice? Are you going to put ice cubes in your lake? So you're somewhat limited there, but you can typically bump up the TH a little higher. But that's the recipe for improving the efficiency. The other thing is, nobody likes a high backwork ratio. because we know that the pumps and the turbines aren't efficient. They're going to have some inefficiencies. We're going to make them as efficient as possible because that's great for performance. But because of the, we want to have a small backwork ratio because we anticipate some inefficiencies in these devices. So how do I reduce the backwork ratio? How do I get that smaller? Well, what is it again? The work pump, work of the turbine. Increase the work of the turbine and decrease the work of the pump. Both ways will help it make the backwork ratio smaller. All right? Well, the goal of this device over here is to boost the pressure. It's got to go, if I don't change these numbers, from 20 kPa to 8,000 kPa. You studied thermodynamics. Given a job to say, I have this substance, I need it to go in this device at 20 kPa and come out of this device at 8,000 kPa. How are you going to do it? How are you going to do it cheaply? How are you going to do it with low work per unit mass? I don't want you to require 275. Can you get that down to 25? Can you get it down to 10 kilojoules per kilogram? What could you get it down to as an engineer? How would you get it down? How are you going to get it down?
Make sure to condense that. Make sure to condense the mixed liquid or the mixed fluid coming out of the condenser more, so that it's pumping more efficiently, because it can't pump the mix. It can only pump the liquid, not the air.
So this is a condenser. If the condenser does its whole job, what comes out of the condenser? Liquid. To boost the pressure of a liquid is a lot less expensive than to boost the pressure of an ideal gas or a superheated vapor or a two-phase mixture. It's a lot cheaper, a lot less expensive. That's a theme I need to drill into you because it's so important. I don't know if I should do it now or later. Do you want me to try and explain why that's true now? Go for it. Okay. Well, I need a clean sheet of paper. Insert new page. There's at the end of chapter 6 in this thermodynamics textbook, they have a general analysis of a control volume in which you have fluid flow in and fluid flow out. And then they say, let's limit this description to int rev, internally reversible process in that system. And then we'll take the first law and the second law, and we'll combine them a little bit with the emphasis on the first law and energy balance, and we'll get an expression like this, lowercase w. What? Work per unit mass coming out, because that's our typical sign convention. And that's equal to W dot per M dot. And that's equal to negative integral VdP, VdP. And then you had also a change in the kinetic and a change in the potential energy. Well, often those are negligible. But it's this integral VdP that is key. Okay, now, first time I saw that equation, I said, no, professor, it's the integral P dV. Now you got it correct. Oh, no. What is it? Is it VdP or PdV? All right, we're going to vote clickers. So version A or version B. You have to find your clicker and vote which is correct. Version A or version B. Done. All right, so now we get to show the results. Everybody hopefully had time to show in. So 78% of the class needs to go and look at section I turned in the textbook, 6.13. Section 6.13. Okay, the section hasn't changed. Maybe the page numbers between editions have changed. I have a previous edition of the text, so I don't call out. But 22% of the class is correct. To understand why it's cheaper to boost the pressure of an incompressible substance versus a compressible substance, we really have to master this concept. All right, so when you see it, you think, this is wrong, it's backwards. This is right. I know, that's why I asked the question. First time I saw it, this is wrong, it's backwards. I understand a piston in a cylinder with a trapped amount of gas, and as I do work, it's boundary work, I have an integral P dV. That's correct for a closed system. Changing volume. But this is a open or a closed system? Open system. Things change a little bit. I don't use U's, I use H's. When I'm looking at the work, it's not the integral PdV. There's no boundary work. Is this control volume expanding? Hold it. Slow down. Is the control volume expanding? Like this control mass was expanding when I pushed back the face of the piston? This control volume doesn't expand. The specific volume may change from inlet to outlet of the substance, just like the temperature may change from inlet to outlet, just like the pressure may change from inlet to outlet. So what I have to do in order to analytically use this expression, whoops, that's the wrong one. This one only works int rev, only if it's internally reversible expansion. That's the best way of thinking about it, even though it could be compression. And now I have to do the integral PdV. So I think about a property diagram. I could do this property diagram. Okay. Well, if I do this property diagram, let me do it for the let me do it for the hard case. Let me put out here the dome. True? When you have a dome on a PV diagram, this side kicks way out. It is not close to symmetric. To make it look symmetric, we'll put it on a log we'll put the x-axis on a log scale. But otherwise, it's really kicked out. It's really stretched. It's very steep over here and very, kicked out over there. That's the true look or shape of a PV diagram. Now, for our Carnot cycle, we started here, high pressure, saturated, that's the state one, saturated vapor, true? And then what did we do? We expanded to low pressure. I got to go from this high pressure right here, pH, to the low pressure, PL. All right, well, where is state 2? Not so easy, because entropy is constant during the expansion from state 1 to state 2. But I recall that the quality was, 70%-ish. So I'm going to kind of show here is state 2, and I know I didn't kick out that tail far enough. I really should kick it out, go like this, and then way out. Okay? So there's state 2. I still don't like where it looks, but it's hard to show things accurately. Whoops, I got to get down to the right pressure. There, that's state 2. This is all the same pressure. That's all the same pressure. Okay. There's state 4. Now, I condense it, but I don't condense it all the way to state 3. I condense it right there. True? Then I boost the pressure. Got it? Now, every one of these are internally reversible. So here's the question for you. How do I calculate this integral VDP? Can I calculate the integral VDP showing it graphically on this PV diagram? Yes, I can. It's a little challenging, because we always were taught to integrate f with respect to x, the integral of f dx. We put x on the horizontal axis, f on the vertical axis. But in this case, I'm looking at it, and I have x on this axis and f on that axis, and I'm integrating f dx. I'm integrating v dp. That makes sense? So to make it look familiar, I got to take this common PV diagram and flip it. Okay, so here's the quick flip. Pressure down here and volume up here. Oh boy. Now, where is the critical point? Here. Okay. This goes way out like that, and then it goes steep like this. Something like that. Okay. Well, that's a bad looking critical point if it's that. Go like that. Right there. Okay? Did I flip it okay? Now I have to find where is my high pressure. Here, here. That state, 4, 1. True? Here's my low pressure. Here, here. And where is my state 2? And where is my state 3? And so it goes like this. I got to pause. Did I flip it correctly? You think so? Now, what I can do is I could say, okay, I'm interested in the work of the pump on this Carnot. Between what states, what was my inlet state to the pump? State. What was my outlet state to the pump? 4. I need to get rid of all this extra garbage. Right? It came out at state 4. True? So now finally, the work of the pump is the area under that curve. Or, if you don't like to flip the diagram, the area to the left of that curve. Going from 3 to 4, going from 3 to 4. So, you say to yourself, that's a big area. I want to reduce that area. So instead of taking a two-phase substance, I'll bring over here saturated liquid. True? If I compress it, that's the new state 3 something. If I compress it, it won't be at state 4 anymore. It'll be straight up to 4. True or false? That area is less than the other area. So this is the key section. Please review it. And to test it, take a couple things. Take superheated vapor. You don't have to have it in the dome. Put state 3 way out in the superheated region. Okay? Put it way out here and compress it up to the same pressure. Okay? You'll find that it's expensive. Take an ideal gas way out. Compress it. It'll take a lot of energy per unit mass of the ideal gas. Take a liquid water. Compress it. Very cheap. Very inexpensive. Same pressure difference. Same pressure difference. Okay? All right. So I guess I tried. Did it help? Hopefully it helped. Let's move forward. Let's put this on a real TS diagram. This is real data plotted as accurately as MATLAB can plot it. Okay? So what was our pressure? Well, first of all, let me review the entropy diagram. You have temperatures, 0 degrees C, 100 degrees C. What is the 100 degrees C? Boiling point of water. What's 0? Ice point. Okay, you look at this, temperature way up here. That's very hot. Okay? Can you have, let's take a look at this point as review. What is the name of this point? Critical point. What temperature roughly is that point in degrees C? 374-ish. True? 375-ish, 374-ish. Can I have, as a review, a two-phase mixture in equilibrium, water at, I don't know, 500 degrees C? No. Can I have water at 500 degrees C and 50 megapascal? Can I have it at a pressure of 500 degrees C and 50 megapascal? Yes, I can, but it's not a two-phase mixture. It's some description. How would you describe water at 500 degrees C and 50 megapascal? It's supercritical. Supercritical. All right. If you kind of get out in this region, let's say it's 500 degrees C and 500 kilopascal. Okay, we call that superheated. Superheated. But it's too close to the dome, so it would be supercritical for the first case. These, I forgot to emphasize, are lines of constant pressure. Why did I make 100 kilopascal a little thicker? Close enough to atmospheric pressure. 101.3 kilopascal is a 1 ATM. So it boils at around 100 degrees C. True? All right, so that's why we have a little thicker. So now what we would do is we would say, okay, well, let's put on this diagram the points for our Carnot cycle we just analyzed. I've got to find a line of 8 megapascal. It's maybe right in here. I bring it down, it's right around there. That's where state 1 is, isn't it? Then we expand reversibly down to 20 kilopascal. Here's the line of 20 kilopascal. Notice its saturation temperature is around 60 degrees C. Come across. Right there is state 2. True? What about state 4? Right there. What did we say the temperature was? Around 295 degrees C. So there's state 4. And then you come across, you stop, and right about there is state 3. You would then put it through that special magical pump to get it to work, to get back up to state 4. So there is the diagram. Does that diagram make sense to you? On a temperature entropy diagram for steam that's drawn to scale. So what I did was I stripped off a lot of the other points and just drew a line of 8 megapascal, put state 1 right there, put a line down to state 2 right there, shown the 100 bar atmospheric pressure, then state 3, then state 4. Got it? Make sense? You could take a look at the magnitudes of the S. They're reasonable, although a different program probably than... this should be very close to the ones we analyzed. And then look at the temperatures, 295 and 60 degrees C. That should work. Also, the quality at state 2 visually and the quality at state 3 should work for that. Now that we mastered that, let me go back to this diagram right here and ask a question. Okay? And the question is I have a failure of a tube in the boiler. It springs a hole. A hole develops in the tube of the boiler. All right? So I ask this question, answer A or B, got a 50-50 chance. A hole develops in the tube of the boiler of this running cycle. Does steam rush out, or does air that's in the room rush in? I develop, unfortunately, a failure, a hole in the tubes of the boiler. Does steam rush out, or does air rush in? So let's show the results. And we have 11% that are Only 4 students are somewhere there. They intended to hit A, of course, or something. So why does the steam rush out of the tubes in the boiler when there develops a failure, a hole? It's a higher pressure. Ready to move on to a practical Carnot?
Is there a situation with atmospheric
Oh, yeah,
pressure?
absolutely. But for efficiency purposes, we want to drop that low temperature below 60 degrees C to 40 degrees C. But if you want to throw away heat to atmospheric temperature, but you're throwing it out of the steam at above 100 degrees C, you're really inefficient. So that's when the condenser pressure would be higher than 1 atm. Let's now talk about the ideal Rankine cycle. What we do is we say we like the boiler. Yes, we like the turbine. Yes, we like the condenser, but we need to let the condenser do all of its work. We need to let the condenser produce saturated liquid. Why? Because that little device called a pump loves liquid. It does not like two-phase fluid. And the work to drive the pump is a lot less if you feed it saturated liquid. Theoretically, it's a lot cheaper to boost the pressure of something that's incompressible than something that's very compressible, like air or steam or two-phase mixture. So it's going to be very efficient to run that pump. We'll still have the fluid flowing in that direction, going around. We'll still call this state 1, state 2, state 3, state 4. We'll still have the heat come into the boiler. Oh, that's going to be the enthalpy 1 minus enthalpy 4. Out of the turbine, that'll be enthalpy 1 minus enthalpy 2. Out of the condenser, that'll be enthalpy 2 minus enthalpy 3. And work into the pump, enthalpy 4 minus enthalpy 3. Now, the cycle efficiency, the backwork ratio, those are all the same. The net work net, those equations haven't changed. What's changed is state 3 is saturated liquid, not state 4. Also, we need to fix state 1. Let's still leave it as saturated vapor, state 1. I know that we're going to superheat it in a minute, but we take baby steps. Okay? Now, I take and make a property diagram, or a table, I should say, of all my states. 1, 2, 3, 4. I then say what is used to fix the state. State 1, what is known? Pressure, saturated vapor. What's state 2? Typically, pressure and entropy. What's state 3? Pressure, saturated liquid. State 4, pressure and entropy. And so we have pressure, temperature, quality, enthalpy, entropy, and you work through and fill up that table. But it's a little different because state 3 is different than the ideal Rankine. When you see ideal, that means it's internally reversible. So the turbine, the S going through the turbine, the S1 and the S2 are the same. Second law analysis around that turbine. S2 is equal to S1. Great. Also, around the pump, S4, S3 is equal to let me do it this way. S4 is equal to S3. Okay? So the S's are the same. So that helps us analyze this system. We don't have any, when it's an ideal Rankine cycle, we don't have irreversibilities in the turbine or the pump. Well, it's named after this individual, Rankine or Rankine. What years did he live? 1820 to 1872, really when the Industrial Revolution really was picking up steam. Oops, you do the math, you do the little difference between the date of death and the date of birth, and you find out that he was 52. That doesn't mean much when you're below that age. It means a lot when you're above that age. True? Yeah, oh boy. He was from Scotland, north part of the UK. Very wide range of interest. Did a very important paper on fatigue and metals, on railroad axles. He was named by Queen Victoria chair of the Civil Engineering and Mechanics at the University of Glasgow in Scotland. In '59, that's why we think about him in thermodynamics, he put out a manual of the steam engine and other prime movers. So from fatigue to thermodynamics, he did a lot. Yes, that is why we honor him with the temperature scale named after him, for the vapor power cycle named after him. And there's still, I haven't attended any of them, but an International Geomechanics lecture series that carries his name. Let's solve this problem. It's the same type of problem, but instead of the Carnot, it's an ideal Rankine power cycle. And we have 8 megapascal for the boiler and 20 kilopascal for the condenser. And we want the same answers. We want the work developed in the turbine, work developed in the out to drive the pump, the heat transfer in the boiler, the condenser, and that. I'm going to jump back, and I'm going to try to, oh boy, I'm going to solve that problem on this page because I have more laid out here. So what would we have for our pressures? Well, 8,000 and 8,000, 20, 20. 295, 295, 60, 60, right? Remember those numbers? All right. Now, what about the quality? State 1, 100%. It's saturated vapor coming out of the boiler. Where else is the quality known? At state 2 or 3 or 4? 3. 3 is 0. It's saturated liquid. So this is H of F at 20 kilopascal. This is S of F at 20 kilopascal, true? And if I go back up here, this is H of G, saturated vapors, enthalpy, and this is S of G, true? Then we would say, I want to get the quality at state 2, that's S of 2 minus S of F divided by S of G minus S of F. And all of these saturated values are at the 20 kilopascal, at the 20 kilopascal, at the 20 kilopascal. And S of 2, we already determined, is equal to S of 1, which is equal to S of G at 8,000 kilopascal, or 80 bar. Did all that make sense? Okay, so you then get that this quality at state 1, let me check, it should be the same as what we had before, 69%, right in that vicinity. And this enthalpy comes in, and these can fill up the table. It's really different at state 3 down here. This is 0. So with a computer program, it's okay to do that S of 3 is equal to S of 4, S of 4 is equal to S of 3, and then ask it to calculate. But what about the state 4? Describe state 4. I ingest into the pump saturated liquid. What comes out of the pump? Saturated liquid. Here's a question for you. State 4, out of the pump. Is it saturated liquid? Is it two-phase liquid vapor mix? Is it sub-cooled liquid, or is it superheated vapor? So what comes out at state 4? What is it? I'll start it now. So you have your clicker question going, state 4, I describe it as saturated liquid, or two-phase liquid vapor mix, or subcooled liquid, or superheated vapor. What comes out of the pump at state 4? All right, polling stopped. So now let's show. Oh, we have a distribution. We have a distribution of responses, do we not?
Yeah.
So what is a different way of saying subcooled liquid? Could I have also said it was compressed liquid? What's the difference? Perspective. That's all. It's either, you could call it subcooled or compressed liquid. It's the perspective. So 54%, congratulations. And how could I tell more definitively? Well, do this. Look on a property diagram. Let me see if I can, forget it. Let me go do this. Here is the solution to the problem that we just worked on. I'll make a couple observations. The S are the same between 3 and 4. This specific volume was much lower, ingesting very dense fluid into the pump. That's a liquid. It kicks out a very dense fluid going out of the pump, essentially incompressible, but not perfectly. Nothing's perfectly incompressible, true. But look at the enthalpy. Goes up some. What about the temperature? What about the temperature? Very little. Very little. It didn't go up a degree C, did it? A half a degree C. Less than a half a degree C. It went up 0.3 degrees C. Okay? You can make the computations here, but what's really stands out? What about that back work ratio? It's 0.9%. Is that a lot or a little? It's very little. Very little. What did it used to be for the Carnot, the back work ratio? 31.5%. A third of what the turbine put out had to go back to feed the pump to make it work for the Carnot. Here for the ideal Rankine, just because it's coming out condensed out of the condenser, the pump takes very little work. It only takes 8 kilojoules per kilogram. So it takes less than 1%, 0.9%. Very little. Okay. That's a big impact. But what about the thermal efficiency for the Carnot? Carnot was 41.4%. The thermal efficiency for this is 34.5%. Is that good? No, it's bad. So, first of all, I have to understand, why did it go down? Was it because the turbine isn't as efficient as it could be? Why did it go down? Is it because of the turbine? A poor turbine? It's all internally reversible in the turbine. Actually, the turbine had the same inputs and had the same outputs. State 1 and state 2 didn't change. Nothing changed with the turbine. It's not the cause. The reduction in the thermal efficiency is not due to the turbine. How about the pump?
Yep.
But I thought we liked it because it takes less work.
Yeah. Thank you.
It's not the pump. The pump is int-rev. Okay, well, what happened different in this condenser? It just condensed more. Professor, the ideal Rankine cycle, it sure would be nice because I recall the thermal efficiency of the Carnot was a nice simple equation, 1 minus Tc over Th. True? Do we have subthermal efficiency at the ideal Rankine cycle, maybe 1 minus T over T or some other simple analytic expression? Do we have anything in our textbook like that? Nope, we do not. Why can't we get something like that? Why isn't this the same? Why is there a difference? There's going to be more heat put into the boiler, that's true, and more heat rejected in the condenser, but when I do the net balance, if it's maximally the best turbine I can put in and the best pump I can put in, why don't I get the same efficiency? I'll give somebody, one person, who would like to try to describe why. They raise their hand, I'll call on them. Otherwise, I have to answer my own question. But here's your chance to try. Anybody? You would like to try? Let's give it a shot.
It's because the QH going in is smaller than the QC coming out.
The QH going in for the ideal Rankine, let's say QB for the boiler, is going to be greater than the Q of the boiler for the Carnot. That's true. That's
I meant that it's smaller than the amount of heat that's being rejected from the condenser.
The amount rejected in the condenser changed, but the amount in the boiler changed too. Both of them have changed.
So does it matter?
I'm looking for something a little more specific as to kind of like, okay, this is the best explanation I can give you. Anybody else want to try? Good try. Yes, sir.
Since the network is equal to QH minus QC, in the way we're condensing it is we have to reject as much QC. So if we increase the amount of QC out, it's not possible that QH could be less than QC, but as we increase the QC out, condensing more liquid, then that would reduce the...
I think you're saying about the same things, and I agree with you. If I could maybe improvise and just put a little scale here. I'm going to put a scale here, and I'm going to say QH, not QH, Q in the boiler. And I'm going to say the Carnot, and then this is ideal Rankine. The Carnot is this much, and the ideal Rankine is going to be greater. It's going to be more. Okay. But then you're saying, look, over here in the QC, we had the Carnot, and we had the ideal Rankine. And on the scale for QC, how much we have to throw away in the condenser, for the Carnot, you had to throw some away, but now you've got to throw more away in the ideal Rankine. So the growth of how much you had to throw out has grown more than the growth of how much you had to bring in. So you're throwing out more proportionally than what you're bringing in. Absolutely true. Absolutely true. But I'm looking for some other explanation, which I'll give you in a minute. It's a little unfair. But you know what? If you read the book, if you actually read the book, all I do is follow the book. Have you figured that out? All I do is follow the book. If you read the book, you could probably, make heads or tails more of what I'm saying. You ever had that where you go to lecture, you understand what they're saying, you read the book, it's like, oh, this book is easier to read now because the lecture helped lay a little forward. You could do the same thing, is read the book before the lecture, and you'll even get more out of the lecture. So anyway, let me do this. I got to go to this diagram. What? What's the name of this diagram? A temperature entropy diagram. And now I really need to expand, and I show you all of these states for the cycles, the two cycles. What did the first one look like? The Carnot. Oh, it had around 8 megapascal. It looked like a box. It went like this. True? Right? What does the ideal Rankine look like? Same state 1, same state 2, so that's not changed, right? But we come all the way over and we condense it to right there. That's new state 3. Instead of stopping there for 3, we go and we stop there for 3. True? The hard part. This is the hard part. Where, don't call it out. Do not call it out. Where is, this is state 4 for the Carnot. True? Where is the new state 4 for the ideal Rankine? Now, this is a clicker question. I will say, let me change color here. The new state 4 for the ideal Rankine, is it closer to A, closer to B, or closer to C? Is it located in the region where I kind of circled point A, circled around for B, or circled around for C? Where is the new state 4 for the ideal Rankine? And I now turn on and give you 30 seconds. Am I out of time? I got a lot more to cover. All right. Now, can all those answers be correct, or is there one answer that's correct and the rest wrong? A. A is correct. Let me go out of here. Read the book. I'm sorry, I'm a minute over. Don't we end at 9:50? And is it 9:52 right now? I'm what? Oh, I have 3 more minutes. Okay, here's the answer. This is state 1 on the ideal Rankine. There's state 2, there's state 3. Do you see the circle? Do you see the circle? Do you see the circle? There's another circle for state 4. Can you see the circle? It is plotted. MATLAB plotted it. Where's the circle? You got to zoom in. All right. So this is zoomed in. This is state 3. This is 60.1. What was that temperature? 60.4 or something. 60.1 versus 60. That's state 4. Go back and look. Yeah, it goes 0 to 100, 100 to 200. No wonder I can't see them, but there's 2 points laid there. Isn't there? So guess what? That's the explanation. This line right here, what line is that? Is that a line of constant pressure of 8 megapascal, 80 bar? It is. So going back here, I go along a line all the way up here. I hit that point. It starts finally to boil in the boiler. What's doing to go here? I got to heat it up. I got to heat it up from 60 to 70 to 80 to 100 to 200. I got to heat it up to 295 before it starts to boil. Am I bringing all of that heat into the cycle at the highest temperature, or am I bringing a lot of heat into the cycle at a lower temperature than TH? What was good for the efficiency? TC, throw it all out at low temperature. TH, bring it all in at high temperature, but I brought in a large fraction of that energy coming into the cycle at a temperature significantly below TH. That's one motivation for the enhancements to the vapor power cycle we study for the rest of the chapter. Thank you for your attention.
Does it say 4S for the ideal Rankine?
This is 4S. Yeah. Straight up on, yeah.